Hello everyone, welcome to the channel of Algocamp. So now on this particular channel, we are actually releasing a series on data structures and algorithms where we are going to talk about some of the most important data structures and algorithmic topics which are extremely important for your upcoming software engineering interviews. Apart from that, these are some of the I would say topics that are very helpful in your day-to-day engineering job as well. We have already released a couple of series around searching, right? And we got a really good response on that. And from here, we are going to put really some awesome content around DSA. In most of these lectures, we will try to ensure that we focus on the intuition building aspect of the things, that how you are able to think about something, what are some of the things that people actually neglect but are going to clear some of the really important fundamentals. We are going to see coding implementation, but trust me, my focus is not going to be on the language delivery aspect of the things, that okay, you have to code this in C++ or Java. A lot of problems we have coded in multiple languages. Maybe some of the problems will be in C++, some will be only in JavaScript. I believe if you are somebody who is preparing for an interview, language in 2025 should not be a constraint, because most of the people can actually use ChatGPT to do language conversions. So my motive here is to make sure that you understand the concept in depth. You actually see how exactly somebody might have thought about the problem when they were carving out the problem, what can be some initial thought process, how you can actually drive yourself towards the solution. I believe these are going to be some really important videos that will be really helpful for your upcoming career. So do let us know what is your feedback. We are going to release a lot of more topics. Do let us know what all topics you want to have first, right? And the feedback is going to be important. Also, in case you are actually thinking to level up, you want to learn things with respect to low-level design, high-level design, overall system design for interviews, or you are somebody who wants to do project development in Spring Boot, you want to learn advanced Spring Boot concepts, or let's say advanced Node.js concepts, then we have a lot of courses, live courses running on algocamp.io. So you can check out the website courses.algocamp.io/learn, and there are a lot of courses that are actually listed. A lot of great discounts are actually going on all the courses as well. Do check them out. For each and every single course, we are going to add you to a dedicated Discord community where you can get your doubts resolved as well. All of the courses, we have made sure that we talk about things from the very beginner to the very advanced level that is going to help you level up in your career as a software engineer. So that being said, let's start the video without any further delay. So this is a new problem coming in front of us, right? We have solved a similar problem previously. So let's try to understand that there are n stones numbered from 1 to n. Okay. For each I, the height of the stone is hi. So there are n stones. There are n stones, 1, 2, 3, so on and so forth, ith stone and then nth stone. There are n stones, and height of each stone is given as h of I. H of 1, h of 2, h of 3, this is h of I, this is h of n. There is a frog who is initially at stone number 1. So the frog is sitting at stone number 1. He will repeat the following action some number of times to reach the stone n. Okay. So in order to reach the stone n, that is frog eventually, once again, the frog eventually wants to reach stone number n, right? For reaching stone n, the frog can do some actions some number of times. What is the action? If the frog is currently on stone I, jump to one of the following stone. It can jump to one of the following stone, either I plus 1, I plus 2, so on and so forth, I plus k, right? So if you are standing at any ith stone, you can go to I plus 1th stone, or I plus 2th stone, or I plus 3th stone, or I plus 4th stone, or I plus 5th stone, and so on, right? At last, final jump that is given to you is I plus k. So, and the cost of every jump is hi minus hj. So before we start this particular video, I wanted to actually talk about a very small thing. So this video is going to actually help you understand a real system design interview scenario. We are going to try to mimic a 45 to 60 minute kind of like a round where we are going to solve a problem very similar to how you will solve a similar system design problem in this short time frame. Now, of course, when you work as a software engineer in a company, you have relatively larger amount of time and you can do a lot of more deep dives in even very small level features. But in an interview, the temperament is different, the approach is different, and a similar scenario is actually explained in this particular video. So do consume the content based on that. Also, if you want to see more deep dives and want to understand these topics in a much more deeper level concepts, then do check out the link in the description section below for our System Design 2.0 cohort, where we have talked about a lot more concepts in a lot more detail, which will make you definitely a better software engineer. So let's just start the video. Where J is the stone to land on. For example, if you were standing on h of 3 and from h of 3 you made a jump to h of 6, then the cost incurred will be h3 minus h6 absolute value, because 6 is the stone you landed on, 3 is the stone that you jumped from. Find the minimum possible total cost incurred for the frog to reach the stone n. Okay, so in this problem you can see you will be given a value of n, which is the number of stones, and then you will be also given height of each stone, and you will be given this value k also, that is going to give you the permissible amount of jumps, that from I plus 1, I plus 2, I plus 3, I plus 4, so on and so forth, up till I plus k, what k you can go to. For example, in this problem, 10, 30, 40, 50, 20. 10, 30, 40, 50, 20. Okay. The value of k is given as 3. That means at any point of time, from any ith stone, the frog can jump to I plus 1, or it can jump to I plus 2, or it can jump to I plus 3. Okay. So what they are suggesting is, let the frog jump from 1 to 2 and then directly from 2 to 5. If the frog jumps from 1 to 2, the total cost is going to be h1 minus h2 for coming from 1 to 2, and then from 2 to 5 if you go, the total cost is going to be h2 minus h5. This is going to be 10 minus 30 plus 30 minus 20. This is 20 plus 10. This is 30. So you can see the final answer is 30. You won't be able to get a cost less than that. For example, let's try any other way. Let's say you go from 10 to 40 and then 40 to 20. In this case, the cost is going to be 10 minus 40 absolute value plus 40 minus 20 absolute value. This is what? 30 plus 20. This is 50. 50 is far more than 30. Right. So any other type of operation you intend to do, in that case you won't be able to achieve it, because this is the minimum possible cost. You cannot do anything better than this. You won't be able to do anything better than this. So any other I would say solution is not going to work, because eventually we want to get the minimum possible value. Okay, so this is the explanation for this test case, and we have to try to solve this problem recursively. We have to try to solve the problem recursively. Right. Now, how can we solve this problem? This is the problem statement. If you want a hint, then I can just give a quick hint that previously we have solved multiple similar problems. So we solved the normal frog jump problem, where from any ith stone you can jump from I to I plus 1 or I plus 2. We also solved similar problem like Fibonacci. So we have solved a similar problem, similar set of problems. Can we somehow map this problem to those problems? Think about it like that. So how can we technically solve this problem? Now we have already solved a problem where we had a frog. We solved it using two approaches, right? We already solved a problem where we had a frog, right? And if the frog was situated at the ith index, then from the ith index, the frog can take a jump to I plus 1 or I plus 2th index. We already solved this problem. And for this particular problem, the recursive relation that we wrote actually in two ways. We had an approach 1 in which we said f of I gives you the minimum cost to reach from I to n, which was equals to minimum of f of I plus 1 plus hi minus hi plus 1, comma f of I plus 2 plus hi minus hi plus 2, right? This was from approach number 1. And then we had another one with approach 2, that is minimum cost to reach from first stone to nth stone is minimum of f of n minus 1 plus hn minus 1 plus hn, comma f of n minus 2 plus hn minus 2 minus hn, right? We wrote these recurrences. Now just tell me one thing. If I change the problem just slightly, if I just slightly change the problem, forget about this problem, okay? Forget about this problem for the timing. Forget about this. If I just slightly change the problem such that now your frog, instead of just going from I to I plus 1 and I to I plus 2, your frog is also having a choice that the frog can go from I to I plus 3. Okay. Let's say I give one more choice to the frog that you can go from I to I plus 3 also. Then how your relations might change, right? You can see it with respect to just the first one, right? So if I change that, then your relation will be something like f of I denotes minimum cost to reach from the ith stone to the nth stone will be equal to minimum of f of I plus 1 plus hi plus hi minus hi plus 1, comma f of I plus 2 plus hi minus hi plus 2, comma f of I plus 3 plus hi minus hi plus 3, right? You will change your relation just like this, right? Because what is this? This is going to give you the minimum cost to go from I to n if you go by I plus 1. This is going to give you the minimum cost to go from I to n if you go via I plus 2. And this is if you go via I plus 3, right? So we can just simply modify this problem and we will get the answer for this case where the frog is allowed to jump from I to I plus 1, I plus 2 and I plus 3. Simple change we can do, right? Because if this solution works for I to I plus 1 and I plus 2, I'll just add one more case that go and bring me the minimum cost. Like what is f of I plus 3? This is an assumption that the function f works correctly for I plus 3. That is, you are going to go and bring me the answer for I plus 3 to n, the minimum cost to reach from I plus 3 to n. And then I will just add my cost to reach from I to I plus 3, right? Simple thing. Now, if I just extend this solution for k, extending the solution for k, right? We can say that now from any ith stone, I have multiple choices. I can go to the I plus 1th stone, I plus 2th stone, I plus 3th stone, so on and so forth, I plus kth stone. So if I want to get f of I, that is the minimum cost to reach from I to n, and if somebody can give me minimum cost to reach from I plus 1 to n, minimum cost to reach from I plus 2 to n, minimum cost to reach from I plus 3 to n, so on and so forth, minimum cost to reach from I plus k to n, then what will I say? I will just get the minimum out of them, because I know my cost is to reach these stones is this. Right. So I'll just add my cost. So I'll say now if I want to go from I to I to n via I plus 1, I have this cost. Or if I go to via I plus 2, I have this cost. If I want to go via I plus 3, I have this cost. And if I want to go from via I plus k, I have this cost. I'll just get minimum of all of them. So I can say that my relation is going to be f of I will be equal to minimum of f of I plus j plus hi minus hj for all j in the range 1 to k, right? I can just write it like this, right? So this will actually become what? Minimum of j starts from 1, right? So I plus 1, this should not be j, this should be I plus j. Hi minus hi plus 1, comma I plus 2. Now j becomes 2, hi minus hi plus 2, so on and so forth. At last j will become k, I plus k, hi minus hi plus k. This will be the value of f of I. So I can write my recursive relations like this, and that's it. That's how we can solve the problem, right? Now you might be thinking, how will we implement it? How will we implement it? Now the implementation is going to be simple, right? Earlier, when it was defined that you can jump from I to I plus 1 and I plus 2, you were manually hard coding this. You were manually hard coding this. This time you cannot just manually hard code this. You have to apply a loop, because you are going from I to some general value k that will be given in the input. So you are going to write something like this. For I is equals to 1, I less than or equal to k, I plus plus, you will get an answer. Let's say it is equals to plus infinity. And then you say answer is equals to minimum of answer comma f of, and this let's make this variable j, f of I plus j plus absolute value of h of my I minus h of I plus j. We just need to put a corner check that if I plus j becomes greater than or equal to n, that is the size of the given set of stones, then we will break, because in that case we won't be having anything. For example, like sitting on this stone, if the frog is sitting on this stone, then you can only make a jump to I plus 1, right? There is no point of making a jump to I plus 2 or I plus 3. Can I say that? We cannot make these jumps. So if I plus j becomes greater than or equal to n, we are going to break. Otherwise, we are going to get the answer from here. That's it. That's it. Everything else is going to be same. This whole thing is going to be wrapped inside a function f, right? This whole thing will be wrapped inside a function f. So just this statement that we were like hard coding earlier, we have to replace this statement with a loop like this, because now we have generalized it that for all j that belongs to range 1 to k. Now 1 to k can be anything, 1 to 10, 1 to 15, 1 to 30. So we don't have a scope of hard coding, but we have a scope of automating it using loops. So this is going to be your general recurrence, or I would say recursive relation. And this is going to be the implementation change that you have to make, and hence the overall problem will be solved.